Welcome to this talk and thanks a lot for tuning in. First, I would like to thank the organizing committee of the Computational Complexity Conference for all their work. And I'm very happy to talk today about the accepted paper, Barriers for Recent Methods in Geodesic Optimization, which is joint work by Cole Franks and myself. So let me give an outline of my talk first. So we start with an introduction to the setting and the computational problems which we will consider. In the second part, I will talk you through the state of the art. So there are certain scaling algorithms and they have a certain complexity to solve these computational problems. And there we will see a certain dichotomy. And the goal in the third part of the talk is to explain this dichotomy via several bounds on complexity parameters. And in this part, I will actually present the main results of the paper. And at the end, we catch a glimpse of main proof techniques, and I will also give an outlook and some open problems. All right, so let's start gently into the topic with matrix scaling. So to recap or to introduce, if you don't know what is matrix scaling, you are given a non-negative real matrix A, and you ask, can we scale A arbitrarily close to a doubly stochastic matrix? So what does that mean? First, a doubly stochastic matrix is a matrix where each of its row sums and each of its column sums is equal to 1. And by a scaling of A, we mean such a product X, A, Y, where X and Y are positive diagonal matrices. And we just do matrix multiplication. And note that we can parameterize capital X and capital Y by small vectors X and Y in R to the N. And we just get the positive diagonal entries via E to the X dot 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 E to the Xn. And yeah, so matrix scaling, to wrap up, is just a problem where we have such an A and we ask, can we find a family of X's and Y's such that in the limit when we perform this product, we get a doubly stochastic matrix. And there's a famous algorithm called the Synchron algorithm, which can solve this problem. Namely, if you can scale a matrix arbitrarily close to doubly stochastic, then this Synchron algorithm will converge to such a matrix. And it's actually a very simple alternating procedure. So you alternate between scaling rows and column sums. So for example, take this matrix A here and scale its row sums so that all row sums are equal to 1. Then synchron scaling scales all the columns. Of course, now the column sums are all equal to 1, but you destroyed the row sums being equal to 1. So again, by scaling via X, you scale all the rows. And then you continue like that. And in this situation, you will actually converge to this doubly stochastic matrix. So this particular matrix is indeed arbitrarily closely scalable to doubly stochastic. And there's a nice important fact which relates it to computer science, namely A is approximately scalable to doubly stochastic if and only if the bipartite graph induced by the support of A admits a perfect matching. And if you look at this matrix and look at its induced bipartite graph, then these red ones will indeed give you a perfect matching. Okay, so in this talk, we actually will study generalizations of matrix scaling. So how are we going to do that? First, we will have a group which acts on matrices or on tensors. And if this group is commutative, then this computational problem, which we consider is actually a convex optimization problem. So this is a really nice situation, which we understand very well. We have truss region methods, ellipsoid methods, interior point methods, gradient descent. So that's a very well-behaved situation. But if G is non-commutative, then we are in the less well-understood arena of geodesic convex optimization. And how fits matrix scaling into this setting? So let's look at this table, which you should somehow keep in mind for the whole of this talk. So matrix scaling arises if the group G is commutative and we act on matrices. And the three-dimensional analog is if we act on tensors, then we get array scaling. So basically array scaling is you act on an n by n by n array. and you act now via capital X, Y, and Z. And you have for each tensor factor, you have such a matrix, and then you want to make it so-called tree-stochastic. So you want to ensure that all slices have sum equal to 1, and you are allowed to slice in any of the 3 directions. So this is then array scaling, and both of these problems also have non-commutative analogs, namely operator scaling and tensor scaling. And all these things have many applications. So this is a highly incomplete list, and it's very due to personal taste. But let me point out that operator scaling became quite famous in the CS community via Edmonds problem, or so-called non-commutative rational identity testing. And tensor scaling, for example, is very important for geometric complexity theory. So for the sake of completeness, let me point out how the general setting is. So SLN denotes the group of complex n by n matrices of determinant 1, and we will also consider the subgroup of all diagonal matrices in SLN. And the commutative group that we consider for our action is just that we have d copies of these STNs, so of these diagonal matrices. And the non-commutative case is just if we have d copies of SLN. And keep in mind that we will act on this vector space. So always think of d equals 2. So then this are n by n matrices, or think of d equals 3. Then this here are n by n tensors. And the action we consider is the most natural one you could imagine. So this is just sending the group element which acts on V to this tensor product of linear maps, and this then acts on my V. So if we have, for example, matrix scaling, then we have just G1 and G2, and then G1 really is just left multiplication on this matrix V, and G2 is just right multiplication via this matrix G on this matrix V. So this is encoded by this action. And I said we want to consider computational problems, actually 2 of them, and we need to define what is the capacity for that. So given such a small v, we call the capacity the infinite norm squared, which we obtain by acting with all our group elements on this fixed v. Yeah, so this is the capacity. And the first computational problem is, given a precision epsilon, we want to approximate the capacity up to error epsilon by some element in our group. So we want to find such a group element such that this inequality holds. And as I already mentioned, if G is commutative, then this is actually convex optimization. Namely, it's an unconstrained geometric programming problem. And in the non-commutative situation, we are in the less well understood arena of geodesic convex optimization. And I hope you agree that if you look at this norm minimization problem, it's very desirable to be able to compute this problem with high precision in polynomial time. And high precision means here that even if I make this epsilon exponentially small in n, I won't still be able to get a polynomial running time in n. So this is why we have this logarithm here. This somehow captures really the high precision in an efficient way. And the second problem that we consider will be the null cone membership problem. This is to decide whether the capacity is 0 or positive. And these two are related, namely the null cone membership problem can be solved if we are able to solve this norm minimization problem up to high enough precision. So at a certain high enough precision, we can really decide whether the capacity is 0 or not. All right, so let's see how matrix scaling fits into these problems. So let's revisit matrix scaling. I said it comes up in the commutative case when d is equal to 2. And if you write out the capacity, then you really see you get a geometric program. So f is our objective function, x and y are our inputs. Yeah? And remember, matrix scaling was the case where x and y were parameterizing via the exponential function our capital matrix, our capital X and our capital Y. And this is then this function, this objective function. And here we see these are the weights for this geometric program. And let me just shortly define it. So this epsilon I is just the ith unit vector up to some shift of the all ones vector. Actually, this detail is not so interesting to understand the talk, but just for completeness, this is the geometric program. These are our weights. And if you have seen a geometric program formulation of matrix scaling, then you might be able to recognize that this is actually matrix scaling for this non-negative real matrix A. So how does norm minimization fit into this matrix scaling case? So norm minimization is now just a question of computing a scaling of A that is epsilon close to W stochastic. And a nice fact about this geometric program is also that we can scale A approximately to W stochastic if and only if the capacity is positive. So since null-con membership was deciding when the capacity is equal to 0, null-con membership translates to deciding whether A is not approximately scalable to W stochastic. So this is how matrix scaling hopefully illuminates these two problems. And then we are looking at the generalization array scaling and also these non-commutative generalizations of operator scaling and tensor scaling. And in all these situations, we have some kind of objective function. And if you take the log and then the gradient, so in the non-commutative case, we call this somehow the moment map. If you look at this and its norm, then it somehow measures a certain deviation. And in matrix scaling, it measures actually the deviation of this scaling from being doubly stochastic. So it's very interesting to note that if you want to decide whether you can scale to doubly stochastic, i.e. whether this capacity is greater than 0, then you can check, can you actually scale this norm down to 0? And this will be important later on for the precision parameter, but we will come to that. So for now, we are done with the introduction, and let me continue with the second part. So let's see what is the state of the art of scaling algorithms and their complexity. So remember, we have the norm minimization problem. We want to solve it efficiently with high precision, i.e. we want to have this running time, and we would also like to solve the null-con membership in polynomial time. And now I have a table here to wrap up all the results. So green indicates we have polynomial time in algorithms, and red indicates we do not have polynomial time algorithms. And the first interesting thing to note is that in the non-commutative regime, we don't have interior point methods available. And actually in the tensor scaling case, we see we do not have polynomial time algorithms. However, in the array scaling case, in the commutative case, we have interior point methods, and they ensure that we have polynomial time algorithms. However, note, it is not known that trust region methods suffice for array scaling to provide polynomial time algorithms. So this is the point where we hopefully see the dichotomy, namely between d equals 3 and d equals 2. For d equals 2, trust region methods both suffice for matrix and for operator scaling. And so the natural question is, of course, can we somehow explain the dichotomy between d equals 2 and d equals 3? Why do trust region methods do not suffice for these problems to give polynomial time? Or maybe do they suffice? Maybe they are actually good enough, but just the complexity analysis lacks to show this. And of course, a little spoiler alert, our results highly suggest that we really need new algorithmic approaches, and that not the complexity analysis lacks to show this, but that it's somehow in the nature of trust region methods that they do not suffice. And how will we show this? Well, we will consider two complexity parameters. So for the high precision, we will look now at the diameter of approximate minimizers. And for the null-con membership problem, we will look at a certain precision parameter, which we call weight margin in our paper for the commutative case, and gap for the non-commutative case. So far, so good. So let's start with the diameter. So remember, we have the norm minimization problem, and we want to find an approximate minimizer, i.e. we want to find a group element such that the capacity satisfies this inequality for this group element here, acting on our given tensor V. And the important intuition is you should think of the diameter as the bit complexity of such an approximate minimizer, but you can also think of somehow this diameter as some distance measure between our approximate minimizer and the identity in our group G. So you also can think of some kind of distance in our group. And the larger this distance is, the worse the situation is. Now, that's basically the upshot. And to define it formally in the commutative case, we just use the geometric programming version of array scaling. So array scaling, similar to matrix scaling, is then this geometric program. Now we have just weights epsilon, I, j, and k. And our inputs of the objective function are just x, y, and z. And similarly, as in matrix scaling, they parameterize our capital X, our capital Y, and our capital Z via the exponential function. And here you should already see why we really mean bit complexity, because our group element basically is obtained, the G1 is obtained by e to the x1 dot 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 e to the xn. So these are the diagonal entries. And so we see that this x somehow captures the bit complexity of G1, and similarly for y and z for G2 and G3. Now we define just the diameter for completeness as the infimum over all radii r, such that whenever we infimize our objective function over the ball of radius r, that we then really find some approximate minimizer, right? So this inequality says that in the ball with radius r, I find an approximate minimizer, but if I want to somehow obtain my actual group element, then remember I need to take e to the x, e to the y, and this is why this actually somehow captures the bit complexity. And analogously, you can define it in a non-commutative setting, but let's not go into details here. Just keep in mind the intuition, and let's look instead at known upper bounds on the diameter. So whenever we act on matrices, we have a really nice situation. The diameter is just polynomially bounded in n and in log 1 over epsilon. So this is a really nice situation. However, if we act on tensors, then we see an exponential behavior, both in commutative and in a non-commutative world, an exponential behavior in our dimension n. And this bound here is taken from Strasser and Vishnoi, and that's just a very general bound for geometric programming. And this bound here is taken from Burgesser et al. And this is a general bound for geodesic convex optimization in this setting. And now a natural question is, well, are these bounds just too pessimistic? Can we actually also make this polynomial here in n and also here polynomial in n? And our first main theorem of the paper is, no, we cannot. So we can give concrete instances of tensors where this diameter is really exponentially large. So we really get this lower bound on the diameter where we see an exponential behavior in n. Note that actually we have to take very, very high precision. So this epsilon is quite small, but it is still in a reasonable regime. And also note that we are not cheating in some way. So this tensor we construct for each epsilon is really well behaved. It has only OM non-zero entries of bit complexity that large. So that's quite good. And also the capacity and also the norm are very well behaved. So it's not that we are like considering an extremely small tensor where you can hardly see the entries. No, we have really a reasonable input and still get a very, very large diameter. And a similar theorem holds in the commutative case for array scaling. And there the theorem is actually a bit stronger because we can somehow drop the dependence of our constructed tensor V on this epsilon. So in array scaling case, we have really a fixed tensor V such that for all of these epsilons, we get this diameter bound. And then the bit complexity is just O n squared log n. So this is all still nicely behaved, the tensor, but we have an exponentially large diameter. So this is actually, yeah, bad news for trust region methods, because by their nature, they usually have constant or maybe polybounded step size, and so they cannot provide high precision for array scaling nor for tensor scaling, because remember, the diameter was like the bit complexity, and if this bit complexity is exponentially large, but we only make constant or a polybounded progress at each step, then we cannot get exponentially far after a polynomial bounded step size, after polynomially many steps. So this somehow really explains why just by their nature, these methods do not suffice. And let me also add for the experts that in the commutative case, our construction actually answers an open problem of Straszak and Vishnoi. Namely, we give a very, very structured geometric program where we still have an exponentially large diameter. And for the non-commutative setting, let me point out that together with the result of Hamilton and Moitra, our construction suggests that maybe even cutting plane methods, as described by Rusciano, may not suffice for high precision. So this main theorem really has several implications and already explains the first part of the dichotomy, namely the one for the high precision. So let's come to the null cone membership. And there, remember, we want to decide whether the capacity is 0 or not. And there we study a certain precision parameter. And let me say this is global in a sense that it does not depend on the given V. And as the name suggests, it captures the required precision that we need to solve the null cone membership problem. And it's also very interesting because the inverse of this precision parameter gamma pi appears polynomially in running time bounds, and it also appears polynomially in a bound on diameters. So the upshot basically here is, if this precision parameter is polynomially small in n, then we are in a nice situation because then the inverse is polynomially large. But if this precision parameter is exponentially small in n, then we are in a bad situation because then the inverse is exponentially large, and then we do not get polynomial running time, but instead only exponential running time for known algorithms. And this is somehow the intuition. It captures the required precision, and it's very important for several reasons to study this parameter. And there are two ways you can define it rigorously. Let's just define it for the commutative case. So basically, this precision parameter is the largest constant with the following property. Whenever the norm of this gradient is strictly less than this precision, then we know that the capacity is positive. And let's interpret that again, remembering matrix scaling. So remember, for matrix scaling, the capacity being positive meant we can scale our matrix to doubly stochastic in the limit. And for matrix scaling, this gradient here somehow measured the deviation. How far are we away from a doubly stochastic matrix with our scaling? So basically, this precision parameter then tells me if I'm not that far away anymore, at a certain point, there's a certain gap. And if I'm below this gap, then I know I can scale this deviation down to 0, meaning I can reach a doubly stochastic matrix. And that is to say the capacity is positive. And this principle generalizes to array scaling, and it also generalizes via the moment map to the non-commutative setting. And the other important description is a combinatorial one. So let's not dive into the details. Let's just look briefly at it. That's very important for proofs. So in general, for a geometric program, we have a set of weights omega. And the precision parameter is then just defined as we look at all subpolytopes. So we take all subsets and we just consider the subpolytopes of the weight polytope where 0 is not contained in, and then we look at the distance to 0, and we take the minimum over all that. So you see that is actually a little bit a complicated definition, but it's a very combinatorial one. So you have the weights, they span a weight polytope. This is the convex hull of omega. And then you can look at all subpolytopes not containing 0. How close can I get to 0? And this is captured by this precision parameter. And this is an equivalent definition to that one here. And for the precision parameter, we actually know lower bounds. So for example, it is known that if we act on matrices, then the precision parameter, both for the commutative and the non-commutative case, is only polynomially small in n. So remember, this was the very nice situation. We get polynomial time algorithms. However, if we act on tensors, then we only know an exponentially small lower bound in n. And similarly to the diameter situation, you could now ask, well, maybe this bound is just too pessimistic. And again, our main theorem for this precision parameter tells us, no, it's not too pessimistic. Actually, whenever we consider array or tensor scaling, this precision parameter becomes exponentially small in n. And we also have an even stronger version, namely if we consider maybe even more tensor factors, so you could also consider 4 or 5 or 6 and so on tensor factors, then we actually show that this precision gets exponentially small in n times d. So if you increase the tensor factors, you make this even worse. Whenever you are at least d greater or equal 3. So this is our main theorem for the precision parameter. And of course, now this bound explains why current methods cannot give polynomial time algorithms for the null membership problem, because we really need a very, very high precision. And it also explains somehow a little bit via these general diameter bounds, why this diameter can be exponentially large for array and for tensor scaling. And with this, we are basically done with the main results. And let's catch a glimpse of proof ideas. So for the commutative case, I hope you have already seen that for the precision parameter, that its second definition has a very combinatorial flavor. And similarly for the diameter, we need to exploit extremal combinatorics. And this sometimes gets a little bit tedious, but it cannot be avoided because you somehow need to really see this exponentially large diameter or this exponentially small precision parameter, and you do not get it for free. So you really have to work and witness this extremal combinatorics. And of course, I cannot explain it here in this talk, but maybe a good intuition or analogy why everything is okay when we consider matrices and why it gets much worse when we consider tensors is the following. So the Birkhoff polytope of doubly stochastic matrices, which I've written down here, is very, very nicely behaved. We understand it very well. And it has several nice combinatorial properties. And basically, the story is that doesn't harm you much. But if you consider the three-dimensional analog, namely this polytope of 3 stochastic arrays, which is also sometimes called a transportation polytope, then this has a much richer and much more extreme combinatorial structure. And this is quite a nice analogy that you can use here to understand why also in our situations, the situation is getting worse when you consider tensors instead of matrices. And for the non-commutative case, well, you could now say there could be a problem because we act by general matrices and not just by diagonal matrices. So the argument could be like this: well, you have a worst case scenario if you act by diagonal matrices, but maybe if you act by much, much more matrices, then you have different directions to go. And maybe there are better directions where you don't have this worst case scenario. And here the notion of a free tensor is very helpful, which is again a quite combinatorial notion. And the basic upshot and intuition here is that freeness somehow ensures that all worst case information is contained in the action with diagonal matrices. And since all our constructions are free, we can lift our free constructions from the commutative to the non-commutative case. But note that actually, since this is also some kind of combinatorial constraint, this adds further challenges to our combinatorial constructions to be actually then able to lift them. So this is then so much about the proof ideas. I hope that's a good guideline when reading the paper. And let me end with a brief outlook and some open problems. So first, I would like to mention that we also have exponentially small upper bounds on the precision parameter when we act on polynomials or on quivers. And of course, there are several interesting open problems. Now I would like to point two of them. So for example, the first interesting question for the diameter bound is, do we really need to take a precision epsilon, which is that small? Or can we, for example, instead of n squared log n in the exponent, just consider n in the exponent? So that would have a positive answer, would have interesting implications. And for the precision parameter, you can, for example, ask the question, we have an exponentially small upper bound, but Burgers et al. Also have an exponentially small lower bound. And what is actually the tied value of the precision parameter between these bounds? So you could specify this a little bit more. And the upshot of the talk is the following. Our results basically show that for tensor scaling, current methods neither suffice for high precision nor for null-con membership. And remember, tensor scaling was the case non-commutative and d equals 3. And therefore, we think that our work strongly motivates the following major goal, to find, namely to find interior point-like methods for geodesic convex optimization, which have a running time which depends polynomially on the logarithm of the inverse of the precision parameter. And current methods don't have this logarithm here. So here, attaining this logarithm, this is like the major goal. Then we would have high precision and null-con membership in polytime for tensor scaling. And yeah, with this, I would like to end and just show you the references which we had on the slides. But please note that we have many, many references, and for a full list, please consider our paper. And yeah, then I would like to thank you for the introduction, for your attention, and hope that you somehow enjoyed the talk.